Would you want to use the microphone?
Okay. Hello. I'm Becky Shantz, and I'm here to welcome Bob Cappetta. And Bob has been teaching at Illinois Community Colleges since 1989. He currently serves as the president of IMAC, the Illinois AMATYC affiliate. He earned a PhD in mathematics education from Northern Illinois University, and his research interests focus on how students learn calculus using the framework Piaget's notion of reflective abstraction. Bob is active at the state level with curriculum articulation. In addition to his interest in calculus, he serves on a statewide panel on developmental mathematics. Please welcome him.
Well, we're here today to talk about calculus. So it's good to see there's a big crowd here. There's a lot of us interested in this topic. And the thesis for my talk today is that infinite series are difficult. Okay? Is this a surprising fact? Let me give you a minute or so to talk to your neighbors at the table to give me 2 or 3 reasons why students have difficulty with infinite series. So see what you can come up with. All right, my friends, do we have some volunteers that would like to share some of their ideas as to why infinite series are difficult for students? Sir?
Because it's abstract.
Abstract. Other ideas?
I mentioned that a lot of textbooks mistreat the alternating series test. They don't do absolute convergence first, and then they do it at the end of the section. And I believe it should be at the beginning of the section, and then you use the alternating series test to determine if it's applied. It's not a convergence condition.
So the notion is the treatment of the alternating series test, and it might be better to reorder the topics in a more natural framework, i.e. do absolute convergence first.
Another thing I do is I start off with Taylor following first and say the goal of all this material is to establish what type of series the representation is function, and then that's why we're going to do all this.
So the next suggestion is do Taylor polynomials first. If I may be allowed to give my perspective on that, why do we teach series? What is the reason for doing that? Why do we spend all our time on the integral test, the p-series, ratio test, root test? The students see no reason for that. Maybe they start to see that with the Taylor series and the Maclaurin series. Other ideas why series are difficult for students? Sir? Oh, it seems very different from the other ideas. Yes? They can't see it. Interesting. Let me ask you this question. When do they see series again after they complete the series chapter in second semester, third quarter calculus? Sir? Okay, in differential equations, we solve second order differential equations using series. That's one place we see it. Is there another place? Sir? Computer science examples as well. Okay, sir? Counting, generating functions. Yes?
If taught properly, they should have seen it in pre-calculus where you're talking about, when you're talking about compounding of interest, that you could build it up.
So examples in pre-calculus as well, with interest and other sorts of things. Yes, sir? Probability theory? Well, I am going to be honest with you. I have a degree in mathematics from the fine University of Illinois at Urbana-Champaign. Please do not harass me about the football team. And I don't think I ever saw series again after I did it in calculus, because I did not take differential equations as an undergraduate. You know, my perspective was primarily theoretical mathematics. I did a lot of algebra and a lot of analysis. I don't think I saw it again. In graduate school, the first time I saw series would have been in complex analysis. And then, of course, we do them in statistics, right? When you take courses in statistics moving on, you have to look at series. But from my perspective, it seemed like an isolated topic that showed up and didn't come up again. So I sort of understand why students aren't real thrilled with the idea. But I believe they're crucial, central to mathematics and what it means. And why do students struggle, and how can we address some of those struggles as teachers? And one thing I like to do when I think about mathematics is put it in a historical context. Do you think series was one of the first things they thought of when they were trying to define things mathematically? How long do you think it took for them to really put series on a firm theoretical foundation? You know, so let's take a look at some of those discussions moving forward. My friend Don Cohen is known as the Math Man, and he works with kids down in Champaign, Illinois. And he has written a book called Calculus by and for Young People, and he has sold more copies of this book in Japan than anywhere else. And this is just one example of what a second grader was able to do to basically show that the sum of 1 over 2 to the n converges, or in his understanding, a half plus a quarter plus an eighth plus a 16th, etc., converges. And that's a beautiful piece of work done by a second grader. If you aren't familiar with Don's work, I'm going to give him a brief commercial here at mathman.biz. Great stuff for kids learning about calculus. And here is his book that is available on Amazon. Here's a little cartoon. The person says, "I keep forgetting, what is the cosine of 60 degrees?" And you can see that the young person's playmate has a somewhat differing perspective than some of us might have. Here's the one infinite series joke I could find. An infinite crowd of mathematicians enters a bar. The first one orders a pint, the second one a half pint, the third one a quarter pint. And you get it. But on a more serious level, I think this is profound. What is it about mathematics that has enabled us to devote our careers to it, to its preservation? What is it about mathematics that inspires us? And this notion that we can capture the infinite in something relatively small, to me, is truly profound. And I think Bernoulli agrees with me, in essence, is saying, just as a finite sum confines an infinite series, and in what has no bounds, there's still a bound. So traces of divine immensity adhere to bodies of lowly kind whose narrow bounds yet have no bound. What a delight to spot the small in vast expanses, to spot in smallness, what a joy, the immense God. Well, I kind of believe in separation of church and mathematics, but the idea that something as profound as infinities, as infinite series, can be captured in a relatively small thing to write, and that students really have a chance to understand, to me, is truly interesting. Zeno's paradox is something I think that all of us know and probably teach. The way I teach Zeno's paradox is, there's a beautiful supermodel at the end of the hallway. I want to go introduce myself. I walk halfway and stop and get nervous, turn around, I get my nerves again, I walk halfway, stop, get nervous, turn around, walk halfway, stop, get nervous, turn around. Will I ever get there? And that is a challenging philosophical question, and it's one that's confused mathematicians and mathematics students for years. I like to talk about Zeno's infinite pizza, something as a Chicago boy I can certainly appreciate. Zeno eats half the pizza on the first day, and then he eats half of what's left the second, then he eats half of what's left the third. So in theory, the pizza lasts forever. But after 3 days, you don't want to eat it. I think we all agree with that. And here's a visual representation of that. Okay, I have a love-hate relationship with Wolfram Alpha. I really do. I believe that students learn by solving challenging problems that take more than 5 minutes to do. So it has been my experience that I would often give projects for students to work outside class, and I would even give take-home exams on occasion. Wolfram Alpha has made that much more difficult. When the students can go ahead and plug a question into a computer and get an answer in seconds, and even show the steps, all of a sudden it's more difficult for me to find those sorts of rich questions that will confound my students and also confound Wolfram Alpha. It's becoming more interesting. But this is one that I think is valuable. Take a look at how we're using Wolfram alpha to sum 1 over n as n goes from 1 to infinity. And if you want to see the world's biggest fractions, just go ahead and change that 100 to 1,000 or 10,000 or something, and notice it gives you a ridiculous fraction. I think a lot of students believe in what I call the nth term convergence test. Students believe if n goes to 0, excuse me, if a sub n goes to 0 as n goes to infinity, the sum will converge. You have to go ahead and correct them on this. And I think using Wolfram alpha, or even using the calculator, you can do this to get approximations on a graphing calculator, helps get rid of that idea. So here's another number, larger number, going to 9.7. Here's another number going to 16.6. Now, this is not a proof, okay? This is not a proof. I do believe that we need to build intuition before we try to prove things. So if we can show for these large numbers that the numbers never seem to stabilize, the students get an idea about what it means, maybe, for a series to converge. The fact that these aren't stabilizing anywhere, they're just getting larger and larger and larger, may indicate to the student that this thing indeed is a divergent series. Now, we know that the sum of 1 over n squared converges, so I do 1 over n squared from 1 to 10,000, I get 1.6448. Now, how many of you know what the sum as n goes from 1 to infinity of 1 over n squared is? Okay. There's a small handful of people. How many can prove it? Most of the hands go down. How many know what the sum of 1 over n cubed is as n goes from 1 to infinity? No one is lying because no one knows what that is. Okay, that's still an open question. So we don't have that value. But it converges to a number, but what kind of a number? Is it a real number? Yes. Is it a rational number? No. Is it an algebraic number expressible as a solution of some kind of a polynomial? No. But it's a real number. And I think that's really the issue that students struggle with. What is a number that's not pretty? What is a number that's not pi, e, or the square root of 2, or a repeating decimal? So I think some of the issues students have with infinite series come with their concerns with numeration. So notice if I added a couple more zeros, the number is stable. And then there's the actual answer. Pi squared over 6. So, back to our basic question. Here is the world's favorite infinite series, a geometric series. A half plus a quarter plus an eighth plus a 16th, etc. When you sum that from 1 to infinity, does it equal 1 or is it less than 1? Simpler version is 0.9999999 forever. Does that equal 1 or is that less than 1? Well, that's at the heart of the question. And some folks have even asked people to teach calculus and they get the wrong answer to that question. If we believe in convergent infinite series, we've got to believe that that thing equals 1. We've got to believe that I actually get to meet the supermodel. All right. How do we actually convince people that this is true? There's several concepts that I believe get in the way. When we teach convergent series, the standard way to teach that is to talk about convergence of a sequence of partial sums, right? We define S sub n, and then we show that the limit of S sub n exists, therefore the infinite series converges. Do you think students really understand that partial sum definition of infinite series? I don't think so. If you're going to do this correctly, to do the first part correctly, you really have to use an epsilon delta definition of the convergent sequence, of a limit of a sequence, which used to be done. I'm not seeing as many people doing that these days, and obviously students struggle with those concepts. Most students believe that 0.3333 repeating equals a third. They don't argue with you on that. They believe that. Their experience supports that. But as soon as you go to 0.9999 equaling 1, that bothers them. But 3 times a third equals 1. So what we're doing is we're creating cognitive conflict. We're creating cognitive dissonance. As was mentioned earlier, my work is following up on Piaget's. And you need to challenge assumptions. You need to give problems that force students to think about their understanding if it's ever going to grow and change. And I think this is the kind of example that can do that. And then fundamentally, do geometric series really converge? We're back to Zeno's paradox. Do they really converge? Do they actually get there? Does that sum exist? Or is it just really, 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 really close? Okay, so here we go. Here's a standard thing that I'm sure many of you have done, either in calculus or even in pre-calculus. The sum as n goes from 0 to infinity of a times r to the n equals that. How do we find the infinite sum? What do we do? Multiply by r and subtract is what I'm hearing from one of the audience members. And there you go. I've got s equals a plus ar squared. rs equals that. And then therefore you get s equals a over 1 minus r. That is not a proof. That is not a proof. That is not talking about convergence of partial sums, is it? Because if it were a proof, 1 plus 2 plus 4 plus 8 plus 16 plus 32, etc. would have to equal -1. Okay. And Don Cohen and his partner Jerry Glynn in Champaign that work in the math program have had many students discover this relationship, that they generalize the geometric series and they prove that infinity equals -1. And they're excited because when you're in second or third grade, it seems perfectly reasonable that infinity would equal -1. Hopefully we know a little better. So here's a more formal version of this. Here's the partial sum perspective, and then we can say, of course, the limit doesn't exist, therefore that infinite series diverges. Telescoping series, something that we often teach. They're kind of interesting, but how often do they really come up? You know, this is one of those things that's in the curriculum, it's in the textbook, but do you ever see them again? Well, but it's a nice application, I'll grant you that, and it's nice to see how it works. But you've got to spend some time setting them up so that they're going to telescope, so that the numerators are the same. And then here's the standard way that it's typically taught. Yes, and we say the sum is 3. And I will say again, that is not a proof. Now, it looks like a proof, but the real issue is that our error terms are shrinking. So we've got to go ahead and express that thing as a limit of partial sums. And then we go ahead and get our answer of 3. Before I go on to the next slide, I don't want you to think I'm pedantic. I don't prove all these things. I let the students use their intuition to solve some of these problems. But I do think it's important on occasion to challenge that intuition with examples. All right. Here's one of my favorite reasons for us to study series. We know that 5 to the 2/3 is defined as the cube root of 5 squared. You learn that in Algebra 1, Algebra 2, early on in your studies. We believe that the function f of x equals 5 to the x is a continuous function defined on all real numbers. But that, my friends, is a belief. Because we can do 5 to the x for any rational number, but how do we do 5 to the x if the number is not rational? What does that mean? How would you compute that? Students don't care very much. If you want 5 to the pi, just do 5 to the 3.1415. Good enough, who cares? Go on. But as mathematicians, we need to have a way to do that, and we do that again with our series. You know, our basic notion for e to the x and then doing the substitution from there. So that's what 5 to the x really means. 5 to the x really means e to the x log 5. Euler's rule. Why do we study series? Euler's rule is wonderful. Some history with me. I never memorized the identities for sine of a plus b and cos of a plus b. When I was in graduate school and I needed them on occasion in statistics or some course like that, I would derive them from Euler's rule. So I think this is remarkably powerful. And can you develop the idea that e to the I theta is cos theta plus I sine theta from the series? And of course you can. We know how to do that. We know what cos theta looks like, sine theta looks like, etc. And we go ahead and get our example of e to the I theta. But then once we're done with that, we've got to recognize why they're important. And what I say is that series are the DNA of transcendental functions. DNA, a small set of information that defines a large person. So we know what e to the x is, we know what sine x is, we know what cos x is, we know what hyperbolic sine, hyperbolic cosine, arctangent, natural log, etc. We know what those functions are. But when you pick up your calculator and you hit those buttons on the calculator, what is the calculator doing? When you ask the calculator to do sine of 30 degrees, is the calculator drawing a triangle and measuring the opposite and the hypotenuse of that triangle? It's using some sort of a scheme equivalent to an infinite series. And it goes out enough terms so that the error is beyond whatever number of digits the calculator is using. So if we think that transcendental functions are important, series are important. And what's the advantage of series? It's easy to integrate and differentiate polynomials. So if you can express something as a series and you want to integrate it or differentiate it, now we actually have a tool that will do that easily. So what seems like a lot of work actually winds up saving us a lot of work as we move on. So here's one of my favorites. If I am ever stuck on a desert island and I really need to approximate pi, this is how I'm going to do it. Now, I will say this is a remarkably bad way to do it, but if you're on a desert island, you have some time. It doesn't converge very quickly at all. There's many better ways to approximate pi. But if you're, a first-term college freshman and you finally learn a way to generate pi, that's powerful. You just go ahead and have them write an Excel spreadsheet and have it do 10,000 terms or 100,000 terms, or even on a calculator. That's powerful. That impresses a student like me, who thinks something that I thought was unknowable before is now something I can get my hands on. That to me is motivating. That to me would help me maybe pay attention a little bit more than I otherwise would have as we talk about these series. The integral from 0 to 1/2 of 1 over 1 plus x cubed. Good luck doing that antiderivative. Okay. Yet look at how simple it is to approximate it to as many decimal places of accuracy as you would like. Now, I don't really think this is a proof either, but it's close. It's close. All right, so here's our favorite series. Everybody's favorite series is a harmonic series. 1 plus a half plus a third plus a fourth plus a fifth plus etc. And we know, contradicting the nth term convergence test, we know that this diverges. And I have to believe you probably teach this the same way I do, where you compare the sum of 1 over n to the integral of 1 over n, and you draw a picture and you show how the sum, all of those boxes are somehow bigger than the integral. And if the integral is infinite, then the sum has to be infinite and it diverges, and isn't life grand? Yeah, that's a nice visual representation, and you do that for sum of 1 over n squared as well, just in reverse. But I like Oresme's proof. Do you see how this is working? 1 plus a half. A third plus a quarter is more than a half. A fifth plus a sixth plus a seventh plus an eighth is more than 4 1/8 is more than a half. A ninth, a tenth, 11th, a 12th, a 13th, a 14th, a 15th, a 16th is more than 8 16ths, is more than a half. You can put these things together in this way as many times as you want, and you always have a string that is more than a half. Therefore, this had better diverge. Historical perspective. So where do we start seeing infinite series? Where do they come up? And I am borrowing heavily from Bagni from University of Udine in Italy. Aristotle talks about it. Archimedes talks about it. Andreas Taquet in the 17th century. Grandi in the 18th century. Leibniz, so what did Grandi say? He said 1 minus 1 plus 1 minus 1 plus 1 minus 1 would have to equal a half. Now, with modern eyes, that seems ridiculous, but he was just averaging. He said it's 1 half the time, it's 0 half the time, therefore the sum, if it exists, it better be a half. It shows a certain amount of insight. I don't want to, insult my fellow Italian there. Leibniz used probability to support Grandi's claim. So Leibniz was with Grandi. Riccati said no, and Gauss, no surprise, who finally defined it correctly, the greatest mathematician of modern times. Gauss was the one to finally put all these people straight. Okay, I just want to ask you this. If the greatest mathematicians in history were struggling with this concept, is it any reason why a freshman at university is going to struggle with this concept? So I think we need to spend a little bit more time on building these concepts and maybe a little bit less time on procedures so that students can get the sort of understanding they need moving forward. There's a citation if you'd like to take a look at some of that history. All right. Sum of 1 over n squared is indeed pi squared over 6, and a few of you recognize that fact, which is good. Euler, another one of our greatest mathematicians, solved it in the relatively recent year of 1735. Jacob Bernoulli, pretty smart person. Leibniz, pretty smart person. Mengele, I assume a pretty smart person, tried to solve that problem and they were unable to prove that it was pi squared over 6. They were unsuccessful doing that. Here's an open problem. Sum of 1 over n cubed is not known. As I mentioned before, in the literature, there are people that really do not believe that the 0.999 repeating is equal to 1. They believe it's less than 1, yet when you give that same problem to those people as a geometric series, they believe that it equals 1. There's your cognitive conflict. That's what you've got to show the students and have them resolve those two ideas. Roe is one of our leading people in the research and undergraduate math ed group talking about series, and she says, some of the misconceptions students have is they believe a series continues endlessly, so it cannot have a limit. Have you seen that before? Like any infinite sum, there's no way it could have a limit because you keep adding more to it. There's no way it could ever, converge. That's a common misunderstanding students have. The second one is the one that aggravates me the most. Plugging in infinity and getting an answer. And then our Zeno's paradox, right? The number gets close, or the series gets close but never actually gets there. That's another common misconception students have. So series needs to get close to a number, arrive at a number, thus resulting in two limits for the series, where a sequence has a limit if differences between consecutive terms get smaller, another idea students have. Alcock talks about an internal sense of authority that enables them to link visual and symbolic representations. Those with an external sense of authority believe that written work is a collection of conventions and procedures. They see no reason to try to integrate visual and symbolic representations. They have no cognitive conflict. If they think their goal is to do whatever the teacher tells them to do, they don't care if in one case 0.9999 is less than 1, and in the other case it equals 1. That's fine with them. One of my goals is to get students to reflect on their thinking, to engage in metacognition. And the only way you do that is by challenging them with these kinds of ideas. What students learn is not what we want to teach. They practice routines. And they think that's what calculus is about. All right. My friend Paul McCombs and I developed a sequences and series concept inventory. And we first used this a couple years ago to determine what students know about sequences and series. And I have to say, I just gave this on Tuesday night, and my numbers are just about the same. I will tell you, when we graded this concept inventory, we were very lenient in the grading. If it was close, we gave them credit. Defined sequences is used in calculus, only 40% could give us an answer. If students said an ordered set of numbers, good enough, correct. Many students gave us sequences when we asked them, gave us series when we asked them to define sequences. 40%, fewer than half, could define sequence. Okay, definitions are hard. We recognize students struggle with that. Second question, construct an example of a sequence. One example of one sequence. 1 in 3, 34% of the students could construct a sequence even though they've been studying them for the entire term. What does it mean for a sequence to converge? Thankfully, more than half got that correct. You know, again, using very, very lenient grading. In other words, you tell me the limit exists of the a sub n, good enough. Define series that is used in calculus, 46%. Less than half could give us any kind of a meaningful definition of series. Construct an example of a series. My friends, how much time do you spend on determining whether or not a series converges? Just asking the students to construct an example of a series at the end of the unit or at the end of the year, we had 51% that could do that, just about half that could construct an example of a series. What does it mean for a series to converge? Less than half. How does a series differ from a sequence? You add the terms. 46% correct. Now, I will grant you the last question on that slide is a challenging one. Construct an example of a series that converges to 4. 23% were correct. Half of them gave us the geometric series. You know what the other half gave us? 4 plus 0 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 plus 0. Which is correct. Construct an example of a sequence that diverges. 29% were correct. Construct an example of a series that converges to 5. 14% correct. Construct an example of a series that diverges. The harmonic series. Only 2/3 could give us one. And maybe the most frustrating question is the last one. Describe the conditions and conclusions of the nth term test. If a sub n does not converge to 0, then the sum of a sub n diverges. 29% could give us a correct answer. And when I gave this to my students on Tuesday, the numbers went a whole lot better. And we just finished the section on series. Okay. In the standard questions, there are certain types of errors that we see over and over and over again. So we're moving away from concepts. I encourage you to give that concept inventory to your students to see if your numbers are any different than mine and to see if there's anything you can do about it to improve those numbers. But if we go to standard questions, you know, sum of 1 over n squared, does that converge or diverge? Your traditional questions. The types of errors that we're seeing in these traditional problems are algebraic errors. No surprise, calculus students struggle with algebra. Calculus concept errors, incorrect conditions or conclusions, choosing the incorrect strategy, stating facts without proof, and misunderstanding the question or the notation. These are the things that we see. And, you know, looking at this, I can't think of many things in the calculus curriculum that have as many potential pitfalls. You know, what do we do? Improper integrals, partial derivatives, maximization problems, epsilon delta definition of a limit. What do we do in calculus that has as many potential pitfalls as doing a standard series question, obviously followed by some missed concepts as we saw in the earlier slides? So to me it seems understandable why the students would struggle. So we've classified the kinds of algebraic errors that we've seen. Exponents, we all know the favorite freshman paradox. X plus y quantity squared is x squared plus y squared. Or in this case, n plus 1 quantity to the n is n to the n plus 1 to the n. Incorrect procedures on radicals, basically the same thing except make it a 1/2 power. So you have that same freshman paradox. Incorrect reduction of fractions. If you're doing the limit comparison test, a sub n divided by b sub n, you've got to know your algebra to be able to reduce that, and many students struggle with that. And then with the direct comparison test, you have to use the inequalities. So you're saying a sub n is less than b sub n. Well, is it? In many cases, students were saying things that just were flat out not true. And I'm not asking you for proof all the time, but at least make sure the statement that you're giving me is correct. So calculus errors. We have to use limits. Limit comparison test, ratio test, root test. You've got to evaluate limits of sequences, not of real numbers. That's a little different than what they've done before. But they've got to do limits. And they can't do them correctly. They don't use L'Hopital correctly. I don't know about you, but here's my philosophy on L'Hopital and series. In my world, n is an integer, and x is a real number. So if a student is going to use L'Hopital to do a limit comparison test, I want that student to change those to x. You know, I know it's a small thing, but you cannot do L'Hopital. You cannot take derivatives if your domain is integers. I don't mark them wrong for that, but it's a cultural thing that I do my best to encourage my students to do. Well, you do the integral test, no surprise they have trouble with an integral. And they also have difficulty with derivatives. So incorrect conditions or conclusions. So here's what I have on this slide. Using the integral test for a series that is not decreasing. Using the LCT when your limit is, you know, not a positive finite number. I should have written it that way. Incorrect conclusions for the ratio root test. So they don't know. Is it less than 0? Is it less than 1? Is it less than 5? Is it greater? They don't know what that is. And then finally, my hated one of all, the nth term convergence test, which of course doesn't exist. Choosing incorrect strategies. So using the DCT instead of the LCT when the inequalities fail. Now, frankly, a lot of students throw away the direct comparison test, and they want to do everything with the limit comparison test. I don't like that either. But if you're not confident about the inequalities, you can get around that by using the limit comparison test. Failure to recognize telescoping series. We had many cases like that, and the students were unable to see it. And another one of my most hated ones, claiming that a geometric series is a p-series. And that's not really that unusual, because a geometric series is something like 1 over 2 to the n, and a p-series is something like 1 over n to the 2. So it shouldn't surprise us that students struggle with that. So my point is, when you're teaching the p-series, I think it's important to step out and say, notice this is different than a geometric series, and here's why. Another favorite student trick is stating facts without proof. Now, I'm not saying that this student is wrong, because 9 to the n minus 4 to the n is greater than 6 to the n eventually. Okay. Clearly, this problem was intended to be a limit comparison test, and the student tried to do it with a direct comparison test. It's not wrong, really, but I wouldn't give this student full credit because he is making an assumption that really needs some kind of justification. Now, what kind of justification he needs, you know, that's something we can talk about. The last thing I have up here is our misunderstanding the question or the notation. So one thing we see often, when you ask students to find the sum of a geometric series, they tell me that it converges. Okay. It doesn't matter if I put some in capital letters with asterisks around it, you know, and bunnies and things. They still answer the question they want to answer rather than the question I want them to answer. They have trouble identifying the common ratio in a geometric series, and that one sort of surprises me, but we saw that often. That they list the first 3 or 4 terms of a geometric series and just can't figure out the ratio. And then if you're doing a geometric series, you need to know what the first term is, right? Our infinite sum is the first term over 1 minus the common ratio. They ignore the index. So if the index starts at 0, well, it's a different starting term as if it starts at 2. So that was another error that we saw that happened often. So you put these two things together. Conceptual errors. They truly do not understand what it means to be a sequence. They don't understand what it means to be a series. Algebraic errors, calculus errors, mistaken conditions and conclusions, misreading problems. A lot of places for this to go wrong. A lot of places for this to go wrong. So as you're teaching this, keep that in mind, please. Recognize that students will struggle. Recognize that students need help on these things. But don't throw it away. I am pleased to say in recent years the AP exam seems to be heading closer to the direction I would like them to head. Because a few years ago they had very few good series questions on the AP exam. Most of the questions were focused on things like intervals of convergence, things that are easy to compute. But they're finally going in a direction that I think is solid. In our classes, right, you know, what are we trying to do? We're trying to teach these folks how to evaluate these infinite series. So what are some teaching techniques that we can use that'll help them do this? A couple of the things I've talked about already. Use things like Wolfram Alpha, use the graphing calculator, have them add up the terms, use a spreadsheet. If the question is, does it converge or diverge, add up the terms. How do you get the difference between a sequence and a series? Visualize it. Put the sequence on the computer. Look at those numbers. Again, a spreadsheet is a wonderful tool. You know, if a sub n is 1 over n squared plus 5, fine. You could run out the first 5,000 terms of that on a spreadsheet if you want, and the students can look at them and see if the sequence converges. Have them understand the difference between a sequence and a series. So use technology to actually go ahead and examine the behavior of those things. Okay. What about those concept issues? How can we get students to do a better job of answering those concept questions? Ask them. Ask them. Ask them early. They don't really show up in the textbooks very often, but ask them in class. Ask them on homeworks. Ask them on quizzes. Ask them on exams. Ask them on the final exam. Ask them in Calc 3. Ask them in differential equations. Ask them. If you want them to understand what a sequence or a series is, you have to ask those conceptual questions. And just because they knew it on Tuesday doesn't mean they know it on Wednesday. So, you know, I have small problems with the Emporium model for learning mathematics, this idea that a student has mastered something and the box is checked and we can move on. Math concepts don't work that way, at least not at this level. So continually ask those questions, you know, give that concept inventory or questions similar to that to your students multiple times. Give them a chance to reflect on those and think about it. I'm also a firm believer in collaborative work. I think students do best when they work together. You can give them problems that are challenging, push them, let them work together, have them try to teach each other how to do these problems. That's, I think, when you see the greatest growth. So indeed, what is to be done? Non-traditional questions. Here's a few. Construct 3 sequences that behave differently. Okay? That could be a sequence that converges. That could be a sequence that diverges. That could be a sequence that converges conditionally. Could be a sequence that oscillates, like Grandi talked about, versus one that goes to infinity. How does a series relate to a sequence? If the sequence converges to 0, does the series converge? Ask that question. And what does it mean for a series to converge? We mentioned using technology to compute partial sums. So if we really do want the students to see that partial sum definition, use technology to get the sum of the first 10 terms, the sum of the first 100 terms, the sum of the first 1,000 terms. Graphical representations help as well. Use questions that challenge faulty concept images. So now we're back to my notion of cognitive conflict. Put students in a situation that they've got to justify their reasoning and reflect on what they've done. Have students generate formal, personal definitions of convergence. If I ask a student, what does it mean for a series to converge, I do not want the textbook definition. That does not show any understanding. Put the textbook away, develop it on your own. Michael Ortman has done some serious work on having students develop these notions of convergence of series as well, if you're interested in reading. And use improper integrals to reinforce the notions of infinite series. So that is my talk. You'll notice the slides are available on the Google site if you would like to copy that down. If you want to use the concept inventory, you certainly have my permission to do so. If you would like to contact me to talk about any of these things, I am certainly more than willing to do that as well. But at this time, I will open the floor to questions, things you'd like to talk about now. Sir?
What kind of format are you giving these concept questions? Are these something that work in groups? Are these something you're standing at the front looking for?
Well, one advantage that I have when I teach calculus, I do it 2.5 hours twice a week. So I think the longer time frame in some respects helps us get into some deeper concepts. So what I typically do with the concept inventory is one day I walk in and I pass out those 12 questions, and I expect the students to do them on their own. Now, many other days, we start classes with collaborative projects. So I walk in at the top of the hour, and the students work on some challenging problems together. That's our usual model. that we have going forward. But I want to see their own understanding. And the thing that's most troubling about that concept inventory is many students leave them blank. You know, I don't mind if you get it wrong, but if you leave it blank, that you don't have enough confidence to at least try to answer that question, that's a problem. And I think I need to work, and all of us need to work on changing the culture so students have the confidence to answer questions that they don't know right away are correct. Other questions or comments? Yes?
A couple of years ago, I talked to an individual that I'm piloting, and I know these apples are also available for different people online, but there's actually some excellent applets in there that they can visualize, and they got it. I was in shock because they got it.
So,
just from being able to see it.
So the point is there are applets available on the internet that help students visualize convergence of sequences and series. That's wonderful. We need to share that information. You know, what can AMATYC do? What can our state organizations do to kind of serve as a warehouse of those sorts of resources so that if someone wants to use them, they know they're out there, and they've been reviewed for being effective. So I think that's a great suggestion, and I think this organization should think about ways that we could leverage your expertise so other people could use that as well. Other questions or comments? Google's a good start if you know what to look for. But see, from my perspective, if we had a teaching series portal on the website, and then we had, this is a good site because, and then people review it. I use Visual Calculus all the time. That's one of my favorite sites. And I can tell you what I like about it and what I don't like about it. So rather than, you know, being a pioneer on the internet looking for things, if I have reviews others have used, to me that would be more effective. Other comments or questions? Sandy, would you like to talk about our symposium? We have, I'll give Sandy the floor for a minute or two.
Coming up, those of you that are interested in modeling the project, in this room we've got Barry Roxwell coming. He's going to be doing a discussion here. The public passes on an AMATYC committee, and we have our committee tomorrow afternoon, but we've got a series of activities symposium this afternoon with Gary, why students do modeling, and then the following one is Sheldon Gordon, and that is scheduled for 1:40. Now, we will be using the technology for that one. We've got Peter's Cross. He is in Long Island with a tree on his roof and still on top of the tree. So he still wants to do this, and so he's working with the hotel, but he will do the technology to kind of do a live feed from his end so that he can do his presentation. His fun, the right courses for the right reasons. So again, taking on the writing mathematical modeling, and then tomorrow morning, I guess 9 to 11, we're going to be doing a 2-hour workshop. It's hands-on. We've got calculators, we've got worksheets. Gary will be leading this, giving the participants a chance to experience some of these problems. Some of them are, word problems type things we've got. Some of them are data collection. Variety that we've been put together for a 2-hour workshop. So we're looking forward to that. And also, like I say, the math intensive committee meeting tomorrow afternoon. Hopefully someone will be available to join us for that discussion of where we're going with some of these colleagues working on talk. Anything else you want to add?
Yeah, I just want to thank Sandy for her leadership. I've been coming to AMATYC for almost 10 years, and I think we've really made a lot of progress in terms of having more talks available for those of us that are interested in teaching calculus. So I applaud her for her leadership, and if you're interested in helping her steer the organization in that direction, please consider coming to our committee meeting tomorrow, as well as our sharing session on Saturday morning. Well, my friends, thank you so much. It's been my pleasure. We'll talk soon.